Okay, so let's continue. So yesterday I stopped just before showing, approving a very interesting form of the steady state of this quantum stochastic process. So we have a spin chain with some interaction, which we are switching on and off via 2-qubit gates using some integrable circuit like XXX. For example, we have now 1, 2, 3, 4, 5, 6, 7 spins, and then the first and the last spin are kind of stochastically coupled via Markovian interaction with the magnetic bats at the two boundaries. And we have described this with this brickwork circuit, where now these guys, all these wires are kind of doubled. I don't want to spend too much time drawing double lines, but you should remember these are now folded gates, and these are Krauss operators which act on the first and the last qubit. And then the ansatz was that the density operator, the fixed point of this matrix, of this Markov process, is of particular form, which is the so-called matrix product state. Or if you want, it's like a Lax operator, or it's like a transfer matrix of an integrable system. Transfer matrix is nothing but an MPS, because it's a product of Lax operators. Each Lax operator acts on two spaces, an auxiliary and a physical space. And physical space is different for each Lax, but auxiliary space is the same. So it's exactly the auxiliary space that people use in writing MPS. So every other one is now shifted by tau. Again, it's a staggered form of this transfer matrix. Sorry, I'm just repeating a little bit so that we get to the same page. So, sorry, this was the so-called amplitude operator, and then the ansatz was that the density matrix is some formal non-equilibrium partition sum times omega dagger, where omega has this form. And this L had this nice structure, which for the XXX model, I'm now just assuming for simplicity we have a simple XXX model. I tell you how to generalize it to XXZ at the end. These charts are really too soft for my hand. So it's a very canonical way of writing the Lax operator, right? This is for any SU2, like for SU2 symmetric spin chain, it has always this form. But now, since the auxiliary space is special, these spin operators are forming a non-compact representation of, or irreducible non-compact representation of SU2. And I will again prefer to use diagrams. Okay, maybe I should use colors, but I will just thicken this line. These horizontal lines are now thicker because they present infinitely dimensional auxiliary space, right? So now this will be like lambda. And then S will be basically the thickness of the wire, right? S determines the thickness of the space, the dimensionality of the space. Anyway, it's infinite, but these spaces are labeled by the representation parameter. Okay, so now this would be like, you can put arrows here just to make it consistent, but otherwise, for most of calculations, we can skip those. Now, let me just use this part of the board to write explicit representation. If you've never seen it, it's very easy to write it, right? You just use SU2 algebra, you use the highest weight state, and you use the fact that the spin has eigenvalue S, where S is a complex number on the highest weight state. So this gives you the explicit representation, namely SZ is this is little s minus k. This is diagonal. The representation is 3-diagonal, of course, in the standard ladder basis. And S plus is a ladder operator which climbs up. Now I won't bother to write them in a form such that one would be the Hermitian adjoint of the other, because this cannot be done. So, I mean, I always can use some sort of gauge freedom to write these two operators such that they look simple. So now I will decide, I mean, usually people decide to write it like that. So now everything is explicit, right? Well, what we need now, I mean, this is the claim, right? This is the claim that the fixed point has this form. And then I will show you how to prove it. Of course, I will not prove all details, but I will show you, I will sketch it how to prove this and similar claims using the, again, Young-Baxter equation, integrability of the circuit. Okay, so what else are we missing now? Yeah, there was one little detail I missed yesterday, and I should correct for it now, namely the amplitude operator has to be corrected by some diagonal twist, which I will write it as D tensor L. So it's a 2x2 matrix tensor L. So it's a diagonal matrix in this computational basis, in the physical basis, where this D is I will parameterize it in terms of some chi, some twist parameter, and I decided to write it like this. So the ratio of the two parameters is square root of chi. The ratio of two diagonal elements is square root of chi. And I will tell you later what chi is. I mean, so now we have parameters, right? These are, now there are physical parameters which determine this problem. What are the physical parameters? These are the gamma right and b right, and gamma left and b left, okay? So this is a driven system. It's driven by unitary fields, magnetic fields, which are characterized by the b left and b right. And it's driven by incoherent processes, amplitude damping processes, which are characterized by these dissipation rates, gamma left, gamma right. So there are four parameters, four real parameters, and these four real parameters completely determine two complex parameters, which are lambda and s. So there is a one-to-one mapping between these four parameters, right, which solves the problem. Which, I mean, the question is, does this exist? Of course, you have to work hard to show that it exists. But this is kind of consistent way of, seeing solution of this problem, right? You have now two freedoms, right? You have spectral parameter lambda, you have representation parameter s. Both are complex numbers. The question is, can you solve your physics problem with this ansatz? Yeah? It turns out, yes, you can, and there is a mapping between this input and output. Yeah? So now, okay, let me just sketch how this works, actually. So, okay, I will just sketch the mapping. The mapping will be, okay, sorry for this is a bit tedious, but okay, I can still write it. I mean, it's not so hard, not so tedious anyway. This is a field, PR, square root 1 minus gamma r minus e to the, then there is a left field, square 1 minus square gamma left, and there is again minus e to the 2i b left, 1 minus gamma left. All right, and there is a very similar expression for the s, where very similar expression for the s, just a plus here. And that's it. And then there is an expression for chi. Well, chi is then also given, chi is a real number, which also gives you, chi is actually related to asymmetry between left and right. So you can basically drive this problem symmetrically or asymmetrically. Symmetrically means that gamma left would be the same as gamma right, and b left would be minus b right. So this would be like a kind of symmetric driving. Of course, driving always means there is a current, but symmetric means that there is down polarization on the left and the same kind of opposite up polarization on the right. This would be like a symmetric driving, and symmetric driving means that chi would be equal to 1. So there would be no twist needed, no diagonal twist needed. But in general, there is a chi parameter which also has explicit expression in terms of parameters of the model. And okay, that is a little bit longer because something like that. Okay, so now this solves the problem, and the question is how we show that this solves the problem. Okay, so now I start using the other board. Okay, I will do that different arrangement later. Well, I mean, the proof uses essentially these relations, which again are universal Yang-Baxter equations, or R-check LL relations in general, which now use a different representation for the auxiliary space. Now remember this, I'm a bit, let me use a color to remind you that, maybe a red color, to remind you that this is a doubled gate, and the Yang-Baxter I will use is a single copy gate. So let me just remind you again, that thing is equivalent to these two copies, guys, right? Because later I will again use operator value. I mean, this folded operatorial gates. But for the time being, I mean, I'm using here. I'm just writing this. Of course, you can always kind of fuse these diagrams into diagrams which into spaces. I mean, such that these are operatorial gates. But I don't want to. I mean, I want to make things as simple as possible. So, so this is the first Yang-Baxter relation that I will use, which is equivalent to one I had yesterday. Well, it's a different version of it, but it's again the same Yang-Baxter equation. It uses a different representation of spaces, right? This one is S, this one is S. 1, 2, 1 prime, 2 prime, 2, 1 prime, 2 prime. And again, I have to use a difference of these two spectral parameters, which is equal to tau, which is the time step.
Wasn't it previously lambda minus tau by 2 now?
Yes, exactly. So now I'm using a slightly different convention of what lambda is, yes. It just means I shift lambda by tau over 2. I mean, I don't know, is there any aesthetic reason behind this? Maybe because I'm now using an odd number of Lux operators, so they start and end with lambda. It's just a matter of taste and feeling of aesthetics, but it doesn't matter. And then there is another kind of property of the R matrix or a gate, which is that it is invariant under arbitrary diagonal twists, meaning that, so this is one relation. The second relation, which I'm using throughout. So now this is our diagonal twist, I call it D. I mean, if you want a formula, this formula means that the gate commutes with the tensor D for any diagonal D, right? This is something you can check in 2 lines, right? I mean, or sitting down at a computer and open Mathematica and check it in 3 seconds. Yeah, so that's something that is always there for the not only for the SU2 symmetric model, but also for the XXZ model. I mean, it has this property. Does it? No, maybe I should be careful with XXZ. Let's say for XXX it's the case. Anyway, okay, so what do we need now? Basically what we need now is to write the full tensor network for the density matrix, because that's easiest. So let me take some space here and write density matrix. Remember, density matrix was omega, omega dagger. So let's start omega, first omega, which is the upper thing. So to make life not too long, let's just take 5 sides. And then there is d square, because I have omega, omega dagger, and from omega dagger I get twist on the left, right? So I have twice the twist on each side. And then I have Hermitian conjugate of these guys. So I have a bit of a problem how to write Hermitian conjugate. So Hermitian conjugate means I take a complex conjugation of all the parameters, and I take the transpose with respect to physical space. Transpose with respect to physical space, I will just designate by putting a little t on top of this diamond, which means I have to flip this diamond vertically, right? So I could also use a wedge here, and then I would put a wedge down, right? Something like that, if you want. And then, of course, I put lambda bar here, lambda bar minus t, lambda bar minus t, lambda bar being complex conjugate lambda. Yes. Is power square. Is power of 2. Yes, it's d square. One comes from, because you see it's omega omega dagger, right? Omega in the ansatz has d on each side, d tensor L times, so d on each side, and then omega dagger has another d, which comes to the left because of Hermitian conjugation. So there are d coming on d, so it's d square in the middle. So this is the sandwich, right? I have to. So now what I have to do, I have to show to you that that actually commutes with time evolution essentially, so that when you conjugate with time evolution and you apply the boundary dissipation, it stays invariant, right? Of course, I will not do this whole thing because I would need a full lecture just for that, but I really don't want to spend more time on that. So I would just show you sketchily how this works. So basically, what needs to do? One needs to, take, for example, when you apply the m, you see you start. M means you write. I see where do you want to start? It doesn't really matter, but yeah, I think you should start like this. Okay, but you do like this, right? And then what you do is you use this kind of relation to push this tau, the gate downwards, right? And now this is, this would be like. I'm now very sketchy, just to show you what this. Sorry, then there is another gate here. Okay, this is from below, and then from above something similar, right? Now one has to be, exactly, yeah. Now, of course, here I should put minus tau. And here I should put whatever conjugations needed. But you see, and the point I want to make is that one uses Young-Baxter relation to push this guy through, and then one uses the second equation that to be invariant under the twist to push it again through. Then you do it also from below, and then you get tau and minus tau, which are inverse to each other because they're unitary and they annihilate, right? Which means that something like, this would be almost like U rho infinity, U dagger is almost like rho infinity back, right? Not quite, because up to boundary processes, right? I mean, this would be if this was a unitary dynamics, right? This means that this would be like an invariant conserved charge, if you want. It would be like an operator which commutes with time evolution. But now we have a boundary processes, so we need also to make sure that once you apply the Krauss operators on the last qubit, then things basically annihilate or cancel the way they should. And this they do exactly when these parameters take the following values. So what I'm trying to say is, yes, this bulk integrability guarantees that you don't have to worry about the bulk. So the problem is just about fixing the boundary. And fixing the boundary solves the problem. Yeah? I mean, then this fixing the boundary basically tells you what are the parameters you have to put into the spectral representation of the algebra. Okay, any question? I have to stop here because I see now I kind of overestimated my ability to explain this in short time, so I need to move on. So, yeah. So, is there any urgent question? Yeah, please.
I mean, so you use these to prove these lambdas and.
Yes, I use these on top of the boundary equations, right? You know, plus boundary equations. I didn't even specify boundary. I didn't even try to write down boundary equations because there would be just, again, lots of notation which I don't want to explain to you. But you remember yesterday I introduced the Krauss operators, exactly how they act, right? So you apply those Krauss operators on this ansatz. Once the bulk is already implemented, then the rest is just Krauss, and this is a single particle condition. It's just condition on the last qubit.
But like, is there any intuition on why lambda and S take this form that it's not symmetric with BL, BR, and gamma L, gamma R?
It is symmetric. Well, yeah, okay. It's just the way it's written. I think they are not. They should be symmetric. I mean, you have to, you know, you multiply by it. You see, there is minus here. So I think, yeah, I think it's just a stupid way of writing, right? Because if I multiply here, but e to the minus 2IBR up and down, you get exactly the same form as this one. I have no idea why I wrote it this way.
Yeah.
It is symmetric. Yeah. Okay. Any other question? Okay. So. Good. So now the question is why do we do this? I mean, why is this interesting, right? I mean, it looks interesting, you know. Okay, there is one appeal of this kind of construction is that it is a kind of direct analog of, you know, stochastic processes. These are quantum stochastic processes which are stochastic only at the boundary, but they are coherent in the bulk. But mathematically, they look very similar to what people have been discussing in the literature of classical stochastic processes like exclusion processes, you know, when you have this problem of transport of particles on a line, which hop stochastically, either the one direction or symmetrically, and then they jump in and out of the system at the boundaries. These models have mathematically very similar solutions than that model, even though it's a kind of simpler. That models are kind of square root of this type of solution. I mean, they have just one copy. We now have two copies because we have density matrix, we have bra and the cat of the density matrix. And so we have this factorization omega, omega dagger. And so things are slightly more complicated, but not much. I mean, again, we use similar kind of algebra representations or whatever of the symmetry of the problem. In XXX case is the SU2. In the XXZ case is the UQ, SL2, quantum group symmetry. But the other point I want to make, again, I want to be very brief. Why is this interesting? Is that it solves a long-standing problem on the ballistic transport in XXZ model. I mean, if you take if you want to apply this to XXZ, what you have to do, you have to just replace the Lax operator of SU2 with the Lax operator with UQSL2. So basically, L then becomes. I will just write that. L then becomes, there is again a nice formula for you remember this notation lambda and eta, which I already introduced yesterday. Eta is related to Q parameter, the formation parameter. And this is like a Lax operator for universal, for let's say for arbitrary complex non-compact spin, where S plus minus Z form a representation of UQSL2. I will not write it down. It is in my notes, but I will not write it down because I don't want to waste time. But you can imagine, right, there is a very similar way of writing generators of UQSL2 for complex spin in terms of three diagonal matrices. And then you plug this in and you get the Lax operator, which satisfies the algebraic relation, the defining relations of UQSL2. And what is kind of remarkable now is that for appropriate values of the driving, so if you take a limit of small driving, you go towards linear response. So you switch off the dissipation in a sense. You take gamma left equal to gamma right, and you let it to 0. And if you want, you take B left equal to B right equal to 0, just to make life simple. In that limit, this problem reduces to, I mean, this actually, the steady state relation actually reduces to something like S becomes small, the complex parameter becomes small, and then you can define an operator which I will call Z of lambda, which only depends on spectral parameter. So now this omega depends again on the 2, so that, it's like a transfer matrix, right? It's a kind of a highest weight transfer matrix because it's defined with respect to an infinite dimensional auxiliary space. You cannot do the trace as usual, but you have to do the sandwich between the kind of ground states, highest weight states. So, but still, it has a form of a transfer matrix. So you take this transfer matrix and you put complex spectral parameter, representation parameter S. You differentiate with respect to this, and then you put it to 0. Okay, I mean, again, I'm doing this, I understand, a bit too quick, but you can imagine, right? I mean, once you study this kind of family of solutions, you can also study the limit where dissipation goes to 0 when this solution becomes trivial, in the sense that, you can easily imagine then when the driving, for example, when driving goes to 0, the solution goes to completely mixed state, to infinite temperature Gibbs state, if you want, to identity matrix. So that actually corresponds to transfer matrix with respect to trivial representation, S equal to 0. And then when you expand around, you get something interesting. And what you find is that if you take time derivative, or if you take discrete time derivative, if you consider what happens with this operator after one time step, and then you subtract this operator, then you find that you get only boundary terms. So you get basically a continuity equation, right? This operator, once it is, this is like d over dt, right? I mean, it's in continuous limit, actually. I'm doing now for the circuit case, but this was actually done first for the continuous time XXZ model, written in terms of Lindblad equation for the boundary dissipation. And there, really, this corresponded to commutator with the Hamiltonian, which means time derivative. So you have a continuity equation. Time derivative of something is boundary terms, meaning that it is something on the left boundary minus something on the right boundary, which is like current, right? Which is like, in and out currents, right, from the system. So in the thermodynamic limit, this becomes conserved. So that is actually something that becomes a conserved charge, but actually it's very funny conserved charge. Because this conserved charge, so let me write a Hermitian combination of that thing. So you take the following object. You take a Hermitian combination of Z and Z dagger, and then of course also that Q obeys similar relation, right? You just take a complex conjugate of the continuity equation for Z. You subtract it, you get continuity equation for Q. And again, it's of the same form. So Q is also conserved. And up to boundary terms. So in thermodynamic limit becomes conserved. But that, what I'm saying is a very kind of nice and funny conserved charge, because it breaks the usual symmetries of all the other conserved charges which are known from algebraic beta ansatz. For example, there is this spin flip symmetry. See, let's call it F, which is flipping all the spins in the Z basis. Right? If you flip all the spins in the Z basis, then all the conserved charges are even with respect to the symmetry. But these guys are odd. This guy Q or Z are odd under this, right? Hamiltonian of XXZ model, or all the charges which I derived yesterday, from the derivative of the transfer matrix, from the logarithmic derivatives, they are all even. I mean, the transfer matrix itself, the standard fundamental transfer matrix, T of lambda, that commutes with F. So it's easy to check because it is formed from a Lax operator which is invariant under this flip symmetry. So, but the Lax operator with respect to non-compact spin is no longer invariant with respect to spin flip, with this Z2 symmetry, this spin flip symmetry. I mean, that's actually a very important observation, and it leads that to the fact that, there is this question of spin transport, and spin transport, is defined with respect to spin current. And spin current in this problem, again in the continuous problem, I will not discuss discrete time problem now because spin current then has to be modified and becomes more complicated, but just for the continuous problem. This is the spin current, and spin current is also odd under spin flip. So which means that spin current is orthogonal to all the standard conserved charges of the theory, but it is not orthogonal to the new conserved charge which we derived from the solution of the boundary-driven dissipative problem. And then this is a big thing, right? Because then we have simple bounds on spin transport, on ballistic transport, like bounds on Drude weights or so-called spin stiffness at any finite or infinite temperature, which results from the fact that we have a conserved charge which overlaps with the current, but overlap is not zero. I mean, there is this Mazur bound, which says that when you have a Drude weight, on Drude weight, so if you have a charge Q which doesn't overlap with the current, so which overlaps with the current where the overlap is not zero, I mean, this thing is just 1 over, well, it's just trace of, so this thing is just expectation value at infinite temperature of some observable, so it's trace of A divided by trace of 1. So there is this Mazur bound. Again, I mean, this was something, again, like a footnote remark. I didn't want to go into any detail here. I just want to motivate why this is so interesting. I mean, it can be used, as I say, in combination with this kind of well-known and old results to prove that the ballistic transport of XXZ should be there. I mean, there should be a ballistic transport of spin current at of spin at XXZ. Well, this only works, of course, in the regime where, well, there is another requirement which I forgot to say, but there is another requirement, namely that Q square has to scale proportional to L. Namely, there is 1 over L here. This guy scales proportional to L, so there is L square here. There should be L here, and this guy should also scale like L, so that the 2L square cancel, and that thing doesn't go to 0. But it can happen that this depends on locality of Q. So this is only true for, let's say, what we call quasi, or sometimes we call only this property, nothing else, pseudo locality of Q. So if you take a non-local charge, then the trace of Q square divided by trace 1 will grow very fast. It will grow as higher power of L, or it will grow exponentially depending on the range of the coupling which you have in this charge. But if you have a charge which is sum of local terms, this will grow like proportional to L. But this charge, which is derived from the derivative of the transfer of this non-compact transfer matrix, can have extensivity in this sense, provided that deformation Q is a root of unity. So this will happen provided Q is a root of unity, which means that eta is I don't know, pi times L over m, where L and m are two integers. Well, this is this is kind of special requirement, but it is actually not so special. I mean, if you are in the regime where delta anisotropy is less than 1, then eta will be real, and any real number can be arbitrarily well approximated by a series of rationals. So what you can do is basically you can take a series of rational approximants of given anisotropy in the critical regime where delta is larger than 1, less than 1, and then for each of those approximations you can provide a rigorous bound and through the weight. So you get a lower bound which is dense in the parameters of the model. Okay, so I mean that's anyway the most exciting application of this type of results. And I mean I probably should keep the rest maybe for tutorials tomorrow if there are questions. I'm happy to explain more. Now I have to move on. So maybe any quick question. Otherwise I have to. Yeah, I already used more than half of the lecture. No, well, there's no actually. Yeah, I mean, I should tell you about situation before 2011, right? I mean, there was a big debate in the community. There were different arguments showing that either transport is ballistic or it is actually not ballistic, just anomalous, but it maybe, numerics suggested ballistic transport, but numerics could be done only for very small systems. And then field theory arguments suggested that both conclusions, depending on the assumptions people made. So it was really a situation which was not clear. And this argument was kind of rigorous argument which settled this debate. It was not surprising. We all expected it, but it was very nice to see it. And it was kind of unexpected, that it came through the study of quantum dissipative system.
And what about delta equals to 1? Is there any regime here?
A very good question. Delta equal to 1 is still open, actually. And yes, so there is, I mentioned probably yesterday the relation to Carla-Parisi-Jeanc scaling of spin transport. And as this is one of being very important questions. And I think this is one possible approach to that question, but I have no idea how to proceed. I mean, the steady state of the boundary-driven XXX does not really seem to be useful. It's not local object, so you cannot use these clean kinematic bounds. You can't separate because it's local, non-local, so you can't separate terms. So I'm happy to tell you more, but that's for the other.
That eta has to be this rational times 5. Is it also connected to that in-string hypothesis? Like if this is not satisfied, you have some weird behavior of the states in the Hilbert space.
I'm not sure I understand your question. I mean, of course, people have then settled this behavior in the context of thermodynamic beta ansatz and generalized hydrodynamics, where in these regimes the strings are the zoology of strings is kind of also strange, right? But everything fits together. I mean, the way they calculate from TBA actually agrees with this lower bound. So actually, this is kind of remarkable. I mean, if you really try to optimize lower bound with respect to everything you can compute from this object, you get a result which completely agrees with TBA, even though it should be, in principle, only lower bound. But it means that lower bound is complete, right? So it's optimal. Yeah, that it takes care of everything that there is. Okay, good. So now I have to change gears and tell you about something completely different. Okay. I will now start talking about quantum chaos in quantum circuits. So forget about integrability now. Integrable systems are nice, right? You all appreciate it, right? I appreciate it, but they're very special. Yeah? Now the question is, what is the other side? What are the typical systems? What are the non-integrable spin chains? How they are behaving, right? I mean, can you say something about that? And this will be my lecture number 3. Dual unitary circuits. So there is of course, I mean, we could give a lot of we could discuss a long time different properties, and there's been actually extensive lectures already in this school about quantum chaos in general, different features of dynamical features of quantum chaotic systems, in particular in lectures of Julian. So we can implement all that in quantum circuits, of course. But what we are really after, I mean, my general title of my lectures is exact solutions, right? Exactly solvable models. So we are really after potentially exactly solvable models of quantum many-body chaos. I mean, this combination of words is actually not as contradictory as it might sound. I mean, there is nothing wrong with having exact solution of a chaotic system. Imagine classical chaotic systems. There are many models in the literature, in the textbooks of classical chaos, which are exactly solvable. I mean, I think most of you who studied chaos theory in one form or another, I mean, they have seen discussions of Arnold cat map or Baker map, you know, simple models on a simple two-dimensional phase spaces. We just take you know, phase space and they map it with a non-linear or linear but strange twisted transformation. And but sometimes this transformation can be linear. Actually, I will tell a little bit about this in my popular lecture tomorrow, because it's very easy and to explain pictorially. But you know, these models are actually can be considered as exactly solvable models because you can derive correlation functions in closed form. You just can't write trajectories, right? Trajectories require knowledge of initial condition to arbitrary precision, require infinite amount of information about the initial condition. This you typically don't have. But otherwise, there are exactly solvable models of chaos. So there is nothing wrong with having exactly solvable model of many-body quantum chaos. It's just that these models have not been around. I mean, okay, depending again on your taste, you may say, yes, but SYK model is a model which is to some degree exactly solvable. It's a model of many-body chaos. Yes, I partly agree with that, only partly, but yes, it's a model of many-body chaos to which you can write a lot of analytic results in the large n limit. But we are really looking for models which are caricatures of statistical physics or statistical mechanics in one dimension or in low dimensions, which means interactions are supposed to be local. So the question is, are there any models which have local interaction, like in 1D or 2D or low D, like circuits which map neighboring qubits and then they operate in a brickwork fashion? Is there a possibility of having such models which would allow for some exact solutions? And the answer is yes, and this is a class of models which were termed dual unitary circuits. And yeah, so what I will do now in the remaining 15 minutes of today and the remaining lecture tomorrow, I will define these models, I will motivate these models, and I will show you first how to compute arbitrary two-point correlation functions, which is the defining feature of these problems. I mean, the fact that the two-point functions can be explicitly evaluated in closed form is the nicest and the cleanest kind of analytical result in relation to dual unitary circuits. But then if time permits, and for sure I will at least give you a summary of that, I would also like to tell you about a less trivial result, which is the proof of quantum chaos conjecture for dual unitary circuits. So dual unitary circuits not only allow us these simple results I just mentioned, but they also allow us to show that the spectrum is given by random matrix. To some degree, I mean, the proof is not, complete in the sense that we cannot prove all the spectral properties are related to random matrix theory, but at least what we can prove is that the spectral form factor, which was discussed again extensively in the previous lectures here, the spectral form factor of dual unitary circuits agrees with random matrices. And that's already, I think, a quite nice and strong result, and it's been only possible for this type of problems. So at least I would like to tell you why this is the case, what are the key features of dual unitaries that allow us to show this kind of statements. Because I believe that this is a good path forward that one can basically try to generalize. I mean, then one can try to generalize it, try to perturb these dual unitary circuits and see whether these results can be pushed further. But anyway, so now this is supposed to be a pedagogical lecture, so I'll give you just these two simple kind of results and try to derive the first one and give you the main ingredients for the second one. Okay, so now, so what I will do now, I will just give you the some, so this will be like subtitle, exact dynamical correlation functions. So anyway, let me give you now some pictures, some compact representation of two-point functions. So we'll be studying what we may call two-point functions. Two-point functions in quantum circuits. So let's define a local observable. A, you put an index j, and that means that A is a tensor product of identity on the first j minus 1 sides, then A, and then another identity on the remaining sides. Let's call them L minus j. So again, the total number of sides is L. So what is AJ? Now let's write tensor network notation for that. AJ is an operator, so it has in and out legs. So there are legs which are just straight lines. The first leg from 1 to j minus 1. And then there is an operator, which is a local operator, which is a single bullet on side j. And then there is remaining ones like that, right? So that is the diagrammatics of a local operator. Of course, we will not use this kind of this kind of straight lines can be usually omitted, right? It's just that we should imagine that this operator is placed at side j, right? And it's a line, right? So now, how do we do time evolution? So let's define time evolution. Now we'll be a little bit more picky with precise definition of time evolution. So we'll define time evolution u of 2t, which will be our u to power t. So imagine u is now u is the same as before. This is a staggered quantum circuit, a brickwork quantum circuit. So it has two pieces of two half time steps, u even times u odd. Okay, and now this will define now a full time step will be 2 time units. So I'll define this like that, and I will I need harder chalks. And then u of 2t plus 1 will be then u to the power t times u even. Okay? Or, no, sorry. Here is a bit of ambiguity. I will take u odd on this part. Okay? And the problem is not translation variant with respect to shifting by 1, but it's only translation variant with respect to shifting time by 2. So when I define it in odd times, I have one ambiguity. I will define it like this. Okay, then I will define then, of course, I define time-dependent operator in a Heisenberg picture, right, as Aj conjugated by u of t. Right. Yeah. So if you want, again, I can split it into an even and odd even and odd times. So at even times, it's very easy. It's just powering our time evolution. This is, if you want, a Floquet operator, right? You power it to time t. But at odd times, you put another piece, Aj So you can take aj of 2t here, and then you. So now let's write a diagram for that. Okay, so it's something like that, and of course you can think of even time steps like layers, right, which are two colored layers, right? And similar to for this guy above, right? So this is basically a kind of tensor network, right? But now you use unitarity, right? What you can do now is you can use unitarity, namely these guys here are Hermitian adjoint to each other, which come here, right? And these are just straight lines, right? I mean, imagine, I will not draw the details, but of course you all remember from my yesterday's lectures, right? I mean, this brickwork has this bricks, right, arranged as gates, right? And then now when you have U and U dagger, then the same gate comes on top of its Hermitian conjugate, so it annihilates, right? And it's instructive to do it on paper by yourself, just to see. I mean, I already mentioned this property yesterday, but it's instructive to do it really, on a piece of paper. And then you see what you can do is basically you annihilate all the gates in the region outside of the cone, right? And here, basically, you have then. Now I'm just doing, sorry for that, but I'm just destroying the picture. Basically, what you have is this type of operator, right, which is now non-trivial only. I mean, now you see this is basically what people call an operator growth, right? You start with a local seat, then apply time evolution. What you get is an operator which is supported on number of steps, which is roughly 2t plus 1. In number of sites, which is roughly 2t plus 1, yeah, in my units now. Because it grows for time. Time is now, one time step is two units, right? So it's four times number of time steps, right? If you want of the full circuit. Anyway, so it's proportional to t. So it grows with the speed, which is well, in my units now speed 1. Yeah. Okay. Right. So you see, I mean, now there is of course an issue. What happens after time, which is equal to the system size? If you have a finite system, then things become non-local, completely non-local after time, which is of order of L over 2, or L over, yeah, L over 4 actually, right? Because it's grows on both sides. So for times, so this is only true if L over 2 is bigger than 2t. Yeah. Then you have a local operator. So operator is still local. Time-dependent local operator is remaining local up to for times which are of the order of system size, one quarter of the system size. Okay, and then I will define two-point function, generic two-point function. Suppose now we have two operators, two local operators. Let's call them A and B. I will define two-point function, placing the first operator at x and the final operator at y. So what I will do now is I will, again, allow me to destroy this picture because of lack of time. But what I will do now is basically, first I write the formula so you'll see what I want. I'll do the following. I will take the expectation value of a product of ax, which is time evolved for t time steps, with a by. Right, so this is 1 over d to the L. Now this is trace 1. I mean, this is finite system of q dits, so dimension of the Hilbert space is d to the L. And then there is a full trace of by u of t dagger ax u of t. Okay, so that's a two-point function, right? Now, these days it's very fashionable to study, let's say, 4-point functions, like out of time ordered 4-point functions. It will be very similar, but then you would just have 4 u's inside, right, back and forth. But now, for the time being, it's interesting enough to study 2-point functions. Okay, and then, of course, to make this story a little bit simpler and pictures nicer and simpler, I will again switch immediately to folded notation. So now what I want, okay, before I go do that, what I want now is basically do the following, right? If I want now replace this with correlation function, what I will do is I will place an operator B somewhere here at the position, this was a position not J, but X now. X and Y are integers for me. So this position X, and now at position Y, I place operator B, and then I do the trace, which means I connect all these wires from bottom and top. And once I do that, then, okay, you will see what I can do. I can also use the light cone from the Y. I can now start annihilating these operators around the Y. So, but looks cumbersome in this notation, so I prefer to use folded picture to do that. So I do folded picture. And then, of course, in folded picture, I will take an operator, Aij, Ij. I represent it as a state. Right, and so what I mean by this thing, I will then transform it to that thing, and that is the same as double wire and a bullet like this. And identity will be just this, and this I will denote as, so this I will just write as this, and then full bullet will be like some non-trivial operator, and empty bullet will be identity matrix, right, or identity operator, right? And I mean, and of course, I will not bother anymore to plot double lines, right? For me now, from now on, everything will be in the folded picture. And when I do the folded picture for the unitary operator, I already explained that, but I just remind you. Sorry, I don't need to do that. This is U and U dagger. This is I, J, K, L. This is K prime, L prime, I prime, J prime. Now I do the folding like this. Then I will get something which I will now write like this. U transpose here and U dagger there. I use a slightly different convention than before. Sorry for that. And this I will then write as W. So from now on, W will be operatorial gate, and the thickness of the wires will be D square, right? The dimension of the wires will be Hilbert space of the dimension D square. So for qubits, this will be 4-dimensional space, which, if you want, is represented by 3 Paulis and identity, or 3 Weil matrices, 4 Weil matrices for C square and so on. So it's a very straightforward object. And then, of course, once I do that, I can represent time evolution. Again, I mean, can do the whole construction of the circuit in operator space. I can construct, again, like W, like script W, which is script W even, sorry, times script W odd. Yes, now there's one thing you have to pay attention to, is that when you go from Schrödinger to Heisenberg picture, the order of operators changes. So before it was odd even, now it's even odd. This is something that you have to work out, but again, I leave it for tutorials if there is still confusion. And W even is again our W tensor L over 2 times. And then we can define W of 2t as W2t and W of 2t plus 1 as WO, now on the left, times W2t. And now what is unitarity of U? It's now equivalent to the following diagrams. You take W, you press unit operator here. I mean, you just press circles, which means that you connect these two wires, right? Because now imagine it's folded. Now if you put here this empty circle, right, it's just like connecting the wires. And now this should be equal to again, two identities, right? It should be equal to identity, which is the tensor product of two identities. So this is like contracting diagrams, right? Now we are basically, what we are doing now, we are developing notation in which everything will be just about simplifying diagrams, right? All the physical observables will plot in terms of some tensor network diagrams, and then we'll have certain rules, right, like unitarity, but there will be some more rules on top of that. Unitarity is useful, but not very useful. It can still leave you with very non-trivial objects. But then we will discuss another property, hopefully not today, I see. We'll discuss another property which will then allow us to contract a lot of things. And this will be basically the upshot of this dual unitary dynamics. Now, okay, just to finish, if I can take 2 more minutes or 1 minute, okay, quickly. Just to have things before I, because otherwise I have to repeat many things tomorrow. So now, I mean, everything is probably super clear already. So I will just now rewrite the correlation function in terms of another diagram, in terms of the diagram in the folded picture, where now it's a single box, where I put W of t, and now there are wires on top, and there are wires in below. And now I put some B here at position, so everything is empty. One B is filled, and one bullet is filled. This is B, and here maybe one bullet is filled. This is A, right? And now again I use unitarity. What does it mean to use unitarity? Which means I use this property. Okay, I have another dual formula to that. The dual formula is I put bullets from below, above, and then I get this. Okay. These are 2 rules, remember them. These are unitarity rules, number 1 and number 2. The rules number 1 can be used to carve a cone like this, right? Number 1 means I can contract from the top. Number 2, I can do from the bottom. So what I get is basically a rectangle, right? So what I get is the correlation function, which is a rectangle. Rectangle of width, which is y minus x, and one direction is y minus x, the other is y plus x. Right? So if y is equal to x, this rectangle is completely linear, right? Which means we are traveling along the light cone, right? If x, sorry, to be careful, I'm doing too quickly. So there has to be t involved, right? So y minus x equal, okay. Let me leave it for tomorrow because I have to. I overspeed it now. Anyway, but the point is now we have this rectangular object, right? And the question is how to contract it. Yeah. So now, of course, this is now, you go back to the unsolvable problem of statistical mechanics in 2D, right? I mean, this is basically an unsolvable problem of StatMech in 2D. It's even worse than StatMech because in StatMech you have positive weights, here you have complex weights. So I mean, to contract this diagram, it's exponentially hard problem. And there is no algorithm, no general algorithm how to do that. So we are now looking for alternatives, and dual unitaries are one alternative which works. So I will continue tomorrow. Thank you. Any question? Yeah.
Maybe I misunderstood. So you have one for the even time steps and odd time steps. You use different evolution, right?
No, I mean, I just use shifted evolution, right? It's the same gate. The same gate is just shifted. The point is that the problem has this staggering, right? Everything is periodic with period 2. I mean, not period 1. If you displace by one side, you have to also go in the time direction by one side. It's this checkerboard. It's checkerboard, but it's 45-degree tilted checkerboard. So
power, it's raised to the power t, or is it transpose? I mean,
Where?
u of 2t
U of 2t,
at the top board.
yeah. U of 2t and top board. Yes. It's power t, yes, sorry. Yeah, it's power t. Because, this is definition of u of 2t is it's time evolution operator for one time step, so it's power to t, right? Yeah. One time step is two steps, actually, odd and even, right? Yeah. And so, so that has to be power, right? I mean, no doubt about it, right?
But in odd, we use the other one.
For the odd, we just supplement it with one half layer, right? Imagine these layers are even, odd, even, odd, even. They always start with odd and end with even, right? So you put odd in on the right, then you have again an alternating structure, right? Okay. It's just that it's a bit tedious because it's staggered, but it's the simplest configuration you can think of, which is discrete.
And what does this bias do in this extra compared to the previous unitary circuits?
What does this?
Previously, we didn't have this extra u or what?
No, it's just a convention how to define time evolution. Before, we were not treating so carefully time evolution, right? We were just discussing more general features of integrable circuits. Now we are really trying to do, honest time evolution, right? The question is, for what models you can actually do time evolution, right? If you ask experts in the integrability, they will just shake heads, right? They cannot do time evolution. So here we can do time evolution. So it's a model which is even more solvable than typical integrable system, right? You can do time evolution, but only 2-point functions. When you go beyond, everything is exploding. Operator spreading is super fast. The entanglement growth is maximal. It's much faster than for random circuits. It's twice faster than for random circuits. So it's like, people like to call SYK model as a maximal chaos, right? Or this model is with the same justice can be called a maximal chaos with local interactions. You cannot have anything faster scrambling than this with local interactions. I'm not yet there. This is still not dual unitary. I'm still just with generic circuits, but tomorrow we are going to. But I'm just making advertisement for why you should maybe be interested in this.
Maybe one weird question. So in classical systems, we have this ergodic hierarchy, and somewhere on the extreme end lies the Bernoulli type systems.
Yeah.
Are these systems some quantum analog?
Yes, they can be treated. I will discuss this tomorrow. I will discuss ergodic hierarchy, and at the very end is what people might call quantum Bernoulli. Yes.
Any other questions?